Hi everyone, I'm David Ozevecki, and with Gustavo Vargas Hakim, we're going to present our paper ClusT3, Information Invariant Test Time Training. This paper had been made at Livia Laboratory, the Laboratory of Imagery, Vision, and Artificial Intelligence in Montreal, and under the supervision of Ismaël Benayed and Christian Desrosiers. Deep neural networks are fragile to the problem of domain shift at test time. The goal of test time adaptation is to take a model trained on a source domain with its label and adapt it to a target domain from another distribution. This without any label and source sample, which make it a very complex adaptation scenario. Test time training is a popular approach of test time adaptation. It used a Y-shaped architecture where an auxiliary task will be plugged to the pre-trained model during training. Then the auxiliary module will be used to update the feature extractor at test time to improve the performance of the model. TTT and TTT++ propose different self-supervised tasks, such as rotation prediction and contrastive learning, respectively. TTT flow uses normalizing flow as domain aligner in an unsupervised way.
Here we show the illustrative example of the information invariant problem in TTT. In the plot A, we see the source and target feature distributions. By maximizing the marginal entropy through clustering, we can split the source distribution in regions with equal probability mass, as seen in the cumulative distribution in plot B. However, when the target distribution is shifted, the clustering of the feature maps is not respected anymore, so that the CDF is not equally partitioned. This led us to devise a way in which we can maintain the mutual information between features and discrete representations that can be clustered. In that way, we propose an information invariant method called ClusT3. Our method maximizes the mutual information between the feature maps and at different scales and discrete latent representations related to clustering. As shown in the figure, we learned to discretize encoding of feature maps in the encoder using a clustering strategy based on mutual information maximization. With the shallow projector, we can map the features into a set of K-cluster probability distribution. The simplest form of the projector is a single linear mapping followed by a softmax. In ClusT3, different projectors can be independently placed on top of different layer blocks of a CNN. At training time, the model learns with a combined loss of cross-entropy and the sum of the information maximization losses of each projector. The hypothesis is that the latent space of the feature maps should be information invariant across domains. Thus, updating the encoder to maintain a high mutual information should also improve classification accuracy. An encoding that better preserves information can be achieved by using a larger number of clusters. In practice, however, doing so might give so poor results, since the constraint of having balanced clusters then becomes too restrictive. We then propose a multi-head clustering strategy where multiple projectors are trained for a given layer, and the loss for that layer becomes the sum of mutual information losses of all its projectors.
Thanks to different ablation studies, we noticed that the best choice for the number of clusters was to take the same number as the classes, and to put the projector on the first layer, layer 1 and layer 2 in the classical ResNet, for example. We also choose to have 15 projectors per layer, and you can find more details in our article about these studies. Here we show some results on CIFAR10C and CIFAR100C. These datasets are corrupted samples from CIFAR10 and CIFAR100. As you can see on the figure on the top right, they had some noise like Gaussian, shot, or impulse noise. On CIFAR10C, which has 10 classes, ClusT3 improved average accuracy by 28% compared to baseline on CIFAR10C. There is also improvement on all the individual corruption type with some exceptions. We also compare with a larger number of classes on CIFAR100C dataset, and our method also beats state-of-art methods. So the information between the feature and their discrete representation, by remaining constant, helps improving the adaptation to corrupted domain. Finally, we use another dataset named VISDA-C, where the training dataset is 3D rendering of 12 different object categories, and the test dataset is made of real images of the same classes. In that case, we use a different projector to improve the result compared to a former architecture. We won about 2% for doing this. And by using two linear layers with a radio activation in between, ClusT3 obtained a gain of 50% with respect to the baseline and outperform previous methods. Thanks for listening us, and contact us if you have any question. You can also find the code and the whole article on the link